this is the most important part in this chapter, so let me repeat it again. So this is the Gauss law, and it tells you that given a Gaussian surface, so you can, given any Gaussian surface, you can calculate the net flux with respect to that Gaussian surface, and that net flux relate only to the charge enclosed by that Gaussian surface itself. It doesn't really matter the charge is distributed here or there, or part of it here, part of it there. It doesn't really matter where the charge is located. It's only related to the total amount of charge enclosed by that Gaussian surface. If some of the charge distribute at the upper part and some of the charge distribute at the lower part, it may be different from all the charge located at the middle part. But the overall net flux will be the same. Maybe for this case, there will be some amount of going outside at the upper part, and there's a negative charge here, so there will be some electric field line going inside at this part, and this part may be more or less zero. But this one only tells you that epsilon 0 is a constant, the permittivity constant. This is the net flux, and this is the charge enclosed. So here it shows that for Gaussian surface 1, S1 is here, and a positive charge is enclosed by S1. So this is a positive charge, so phi 1 should also be a positive value, which means that the electric field line is flowing out from this volume. And for phi 2, this is a negative charge. This is S2, so phi 2 should be negative. Which means the electric field line flowing in this volume enclosed by S2. And for phi 3, phi 4, actually this one is S3, so it encloses nothing, although there are positive and negative charge close to it, but it is outside S3, so phi 3 should be 0. And for phi 4, which is the largest part, it encloses both the positive and negative charge, so the total amount of charge inside S4 is 0. So phi 4 is also 0. So that is what we have mentioned on Tuesday. So next, we talk about the relationship about the Gauss law and Coulomb's law. Actually, Coulomb's law is included in the Gauss law, which means that if we assume Gauss law is correct, and actually it is correct, then actually we can really derive the result of Coulomb's law. So this is how we derive it. So the first line is actually this part equals this part is actually the Gauss law in the previous page here. So actually we define the Gaussian surface to be a sphere, and a positive charge Q is at the center of this sphere. So actually, due to the symmetry, we will know that the E field should be pointing outward, and actually which will have the same direction with the area vector. And so the inner product for E vector dot dA vector will be nothing but EDA, or you can just multiply cosine 0 degree. Cosine 0 degree is actually 1. So as long as they have the same direction, so you just multiply by 1 for the projection component. So we will have the net flux like this. Actually, the inner product means you have two vectors and you finally come out with a scalar. So this is like this. And then we know that due to the symmetrical properties, the E field should be uniform over the whole surface, because the distance from the center to the surface should all be the same. From here to there, from here to there, all should be the same. There should be the same distance between them. So E will be a constant, which means that we can just pick E out and we just integrate the surface area. And actually, the surface area of a sphere is 4 pi r squared. You should learn it in calculus class, or maybe high school you should have learned that. So actually, this one should be 4 pi r squared. So we substitute it here, and finally we subtract epsilon 0 4 pi r squared on both sides. Then we will get this. So this is E equals KQ enclosed over R squared. And actually it is nothing but the first, maybe the first, not really the first, actually is what we have in chapter 22. And so it is actually the same equation like this: Q1 Q2 R squared. So this is the Coulomb's law, and you can regard Q enclosed. Maybe I can. This is Q enclosed. So maybe you can let Q enclosed is Q1 and the test charge is Q2 here. So you have Coulomb's law. So actually these two is actually the same. So we can have Gauss law, and then we can derive the Coulomb's law. So which means that Coulomb's law is a special case of the Gauss law. Any questions? Or in other words, if you can use the technique you learned in the previous chapter, or you want to calculate the E field generated by some charge distribution, actually using the Gauss law, if it is calculatable, then you will get the same results using the Gauss law, or using the technique you learned in the previous chapter, and then you do integration, something like that. So let's have a sample example. Okay. So in cross section, plastic sphere, spherical shell with uniform charge Q and radius R. Particle with charge Q is this one. Q is this one, or this one. At the center of this sphere. Actually, this is just a cross section, so it's just look only like a ring, but actually it's a whole sphere. What is the electric field? Magnitude and direction at point P1 and P1 for part A, and P2 for for the next slide. So we calculate the E field at P1 first. So we use the Gauss law, of course, and we should actually define the Gaussian surface here. Gaussian surface here. It is also a sphere. Maybe I use another code. Yeah, I use green. So actually, we can also. This one is the Gaussian surface we define for this question, and this is it is also a sphere. Actually, when you use the Gauss law, you need to define the Gaussian surface first, and it could be drawn here. But actually, when you consider the whole graph, this one is actually this one, because we concern the point here. So we define a Gaussian surface with the radius equal to this one. So P1. So this R1 is this one. So we use the Gauss law. So we have epsilon 0 surface integration E dot dA equals Q enclosed part A. So actually, this is uniform. This is uniform because this is actually at the center. So we should have E should be a constant. So we can just pick it out, and we have dA, and actually the charge enclosed by this Gaussian surface is the small q. It's the small q. The capital Q is outside, so the overall force contributed by this charge should be 0. So actually, this one should be 4 pi r1 square q, 4 pi r1 square, and equals q, something like this. So actually, E should be 4 pi epsilon 0 E. Sorry, not E, Q plus Q over R1 square, and we substitute all the values, 8.99 times 10 to 9 times Q is 5e, which means it is 5 times 1.6 times 10 to minus 19 over R1 6 cm 0.06 square. So the answer will be 2 times 10 to minus 6 n over c. Or you can write 2 mu nc. Or you can write 2 mu nc per c. You can choose either one. You don't really need to write both. And for the quiz, I suggest you should write as complete as possible. Which means that you should try to write the equation, or if you can try to write how you derive it, and then you substitute all the values and then you come out an answer. Don't try to just give through this step and you write something and then you just jump to an answer. If it is correct, it will be okay, but if it is not correct, then I will not know whether you substitute the correct value into the equation you write. Then it's possibly you be more point will be deducted. So try to write as complete as possible, unless you can guarantee what you write should all be correct. Okay. So for part B, actually first part should be the same, but here we calculate the E field at point P2. So here we define the Gaussian surface here. So this is R2, this is R2. And similarly we can actually write the same procedure like this, and finally will come out E would be something like this. This will be R2 square, and the Q actually this part will be the Q enclosed by the Gaussian surface, and for this case, the enclosed charge for this Gaussian surface should be small q plus capital Q. Okay, because both of them are enclosed by this Gaussian surface. So we substitute 8.99 times 10 to 9 multiply minus 16 plus 5, 1.6 times 10 to minus 19, and R1 is 0.12 squared. So the answer will be minus 1.1 times 10 to minus 6 and over C. So actually, if you just draw it out, it will be something like this. This is R axis, the distance from the center, and it will be something like this. Something like this. So this one is 5ek over R squared. This one will be minus 11e k over R squared, and this is 10 centimeter. So if you just draw it up, it will be something like this for this case. And so far, any questions? Okay, so next one. So what is the net charge enclosed by the Gaussian cube? So actually the same graph as in SP 23.02. So at that one, we have calculated this one, and this one. And it is obviously that front and black. This should be back. This should be back. This is fronts. This is back. How to draw back? Maybe I can draw like this. So this one will be the back. This one will be the back. Because E should be only in X and Y direction. So front and back, for the front, DA should be point to the positive Z direction. For back, should be point to the negative Z direction. So you don't really need to calculate. It's obviously these two are also 0. So what does it mean? Okay, maybe I can still calculate the bottom part. Actually, I can still calculate the. It asks you what is the net charge enclosed by this Gaussian cube. So actually, we can still calculate the total flux for the bottom part. Which is bottom EDA, and so actually, so let me just erase this out. Okay, so for the bottom part, DA should be point to the negative Y direction, which means, and actually, so it is actually DA multiplied by the minus J vector. So so in Y direction it is 4. So E should be 4, and DA is actually, this is 4 millimeter square. So we multiply that by another 4, and this one points to the positive Y direction, and this one points to the negative Y direction. So that when they have inner product, we multiply by -1. So this one should be 16 nm square over C, and so we get the total flux for this Gaussian surface would be -12 plus 36 plus 16 plus 0 plus 0 plus 16. So the answer is 24 nm square over Coulomb. And actually, Q enclosed should be epsilon 0 50, which is 8.85 times 10 to minus 12 times 24, which is 2.1 times 10 to minus 10 Coulomb. Or you can write it as 210 picocoulomb. So this is just a simple demonstration for the Gauss field, which means that you can calculate the net flux, then you know the total charge inside this volume. But actually, you don't really know how the charge distributed. You only know the overall charge inside. You don't really know whether it is all distributed here or there. So any questions? Okay, let's continue. Next we talk about a charge isolated conductor. Charge isolated conductor, which means this one, this green plane, and we have assume for this case we have a positive charge here, and conductor is a very important keyword. Conductor. For conductor and insulator, they are different. And for this case, so here shows a side view of a tiny portion of a very large, actually infinite large, isolated conductor with excess positive charge on its surface. So a closed cylindrical Gaussian surface embedded perpendicular in the conductor， 有一个圆柱体，然后垂直这个面的。So embedded perpendicularly in the conductor enclose some of the charge, and the E field line pierces the internal end of the cap and cylinder. But the internal end cap, the external end cap has area A, which means that this part, the top part, has an area of A, and the area vector A vector. So the point here is that for a conductor, suppose it has some thickness for conductor, all the charge should be distributed on the surface only. If the charge will not go inside, will not be distributed inside for the steady state. 电荷就会跑到那个一个固体的表面，或者如果里面有一个空腔的话，会跑到那个空腔的表面。Okay, so actually the charge will only distribute on the surface or the surface of the cavity. So for this case, we apply the Gauss law here. And actually, suppose on this side we have on one side we have epsilon 0 multiplied by the total flux, and actually there will be no E field inside a conductor. There will be no E field for conductor. But for insulator, there may be E field inside. So you may need to remember this fact. There will be no E field inside the conductor, no charge inside the conductor. So and actually we'll know that all the E field generated by these charges will be perpendicular to this surface. So there will be no net flux contributed by the side of the cylinder. all the net flux contribute to this whole Gaussian surface will only be this part. Will only be this part. So actually, the E field times the area of this circle. So the Q enclosed would be the surface charge density multiplied by this area. So we have Q enclosed equals sigma A. So we can just cancel A because we have A here. So we divide epsilon naught on both sides. So we have E equals sigma over epsilon 0 for a infinite large charge isolated conductor plane. So the E field would be sigma over epsilon 0, which is a constant. Generate a uniform E field. So if you can still remember, in chapter 22, we have learned the electric field due to charge disk. In charge E field generated by a charge disk, and as long as we have charge disk, and as long as R is infinity, the E field would be something like this. And there is a factor of 2 here, because in this case, this disk is infinite thin. So for this case, if we consider the cross section, suppose we consider the cross section. Maybe I just put the disk something like this, and then it goes to infinity. So, but I cannot draw to infinity. So just imagine it is infinity. So it will generate the E field on the top, pointing upward, and generate the E field pointing downward at the lower part. So which means that in this case, this will have half of the E field, this will have half of the E field. So for this case, we will have a factor of 2 here. But for this case, we consider this is thick. So for this part, there will be no E field. So all the E field are concentrated at the right part. So it is 2 times larger. So any questions? Okay. So here's another sample problem. Actually, it's not difficult. So here we have the figure shows a cross section of a sphere. Still a cross section of a spherical metal shell. The inner radius r, and upon charge -5 μ Coulomb is located at distance. So it is not actually placed at the center. This is the center from the shell. If the shell is electrically neutral, so there is no net charge on this shell. So what are the induced charge on its inner and outer surface? Are those charges uniformly distributed? What is the field pattern inside and outside the shell? So actually, the point here is that this is a conductor. So if we define a Gaussian surface inside this shell, there should be no E field. There should be no E field in this shell. Which means that the the net flux for this Gaussian surface should be 0, which means that applying the Gauss law, the charge enclosed by this Gaussian surface is also 0. It's also 0. And we have a negative charge here. We have a negative charge, minus 5 mu c is located here. So there should be a induced positive charge in the inner surface. So that which makes the total charge inside this Gaussian surface to be 0. So the inner surface should have a induced charge positive 5 mu Coulomb for the inner surface, and it is actually not uniform distributed. Suppose the negative charge is close to the left side, so for this part the charge will be the induced charge will be denser, and for these parts they will have less, that it will not be so dense for this part. And actually the shell is electrically neutral, which means that for the outside surface, the negative, there will be a negative induced charge for the outer surface, and this part would be uniform distributed. The negative charge should be uniform distributed. So for the outside, when you see this, you will consider it is there will be only a negative 5 mu c actually located at the center. If you just see this stuff outside, because the E field generated by this stuff will generate an E field which will be exactly the same as all the charge located here. So it's just like a shield. 像一个盾牌. You cannot see where the charge is. You not see where charges. You feel like the charge is actually located here. So up to here, what you need to know is that inside the conductor there will be no electric field and no charge. And actually for a conductor there will be free electrons, so there may be induced charge due to other charge placed close enough. So next we talk about let me talk this fast first, then we have a break. So next we talk about applying the Gauss law with the cylindrical symmetry. 椭圆形的对称. So in this part, we want to calculate the E field generated by a infinite long plastic rod. It is actually plastic rod with a charge on it. So it will generate a E field, with the uniform charge density lambda. The charge distribution field have a cylindrical symmetrical, because as long as you consider this line is infinite long, so For here, you should see the same E field for this point with the same distance from it. So it should be a cylindrical symmetry. As long as the R is equal, they should have the same E field. They should have the same E field. So in this case, we define the Gaussian surface as a cylindrical. And you can also imagine all the E field should be perpendicular to this line, because you can imagine, suppose point to here, and maybe I use the blue color. So suppose I go up for let's say A, and go down for A also. So for this part ds prime, it will generate the E field at maybe this point, something like this, and for this part, it will generate a E field like this. So for the vertical component, they should be cancelled, and only the horizontal. Actually, the horizontal, but I need to draw it in 3D, so it is not. Really that good. Maybe just consider this is not 3D. So actually, all the vertical components are cancelled, and actually, the E field should be horizontal. Which means that the only point to the R direction. So we apply the Gauss law in this case, and this is still epsilon phi, and phi would be EA, because E is uniform at the side, and there will be no electric flux contribute for the top part and the bottom part, because all the E field are perpendicular to the line. And for the top part, the dA should be pointing upward, and for the lower part, the dA should be pointing downward. So there will be no left flux contribution for the top part and the bottom part. There will be only the side part contribute to the net flux. And we assume that the area of the side is A and Q enclosed. So let me consider this part first. Lambda is the linear charge density of this line, and h is the height of this cylinder. H is the height of this cylinder. So for the area, it is actually you can cut it out and then you can expand it. So it is a rectangular. The height is h, and the width of this rectangular would be this circumference of the circle, so which is 2 pi r. So the area of the side part would be the width times the height, 2 pi r h. This is the width, this is the height. So this is the area of the side area. And actually h can be cancelled, so which means that no matter how high the Gaussian surface is, it doesn't really matter, because it shouldn't matter, because we consider the plastic wad is infinitely long. It shouldn't related to how high we choose the Gaussian surface. And so h can be cancelled, and then we divide epsilon 0 2 pi r on both sides, so we have the E field generated by the infinite long plastic rod would be like this. The lambda is the linear charge density over 2 pi epsilon 0 is a constant. It's a constant. And R would be the distance. The distance from this rod. So actually it is inverse proportional to the distance. Inverse proportional to the distance. This part would be, maybe you can still consider this as a constant, but it relates to what is the total charge, on this, or the charge density. Actually is infinitely long, so the total charge on this rod should be infinity. So it relates to the charge density and inverse proportional to the distance.